If there is one thing Albert Einstein taught us, it is that time is an illusion. It is flexible, relative, and often entirely dependent on the perspective of the observer. Yet in the story of his own life, there was a relentless, ticking quality to the clock, a pressure that shaped his destiny long before he reshaped the cosmos. We begin not with the genius, but with the rebel, not with the universe, but with the defiant, quiet boy who refused to be contained by the rigid world into which he was born. He arrived in Ulm, Germany, in 1879, a time when the invisible forces of electricity were transforming civilization. His family, though immersed in the age of engineering, saw a child who was unconventionally slow to speak, reserved, and prone to long, silent fits of contemplation. This initial slowness was, in retrospect, the earliest sign of his mind's unique pacing, a mind that demanded deep, internal structural coherence before it would commit to external expression. His world was suddenly and profoundly clarified at the age of 5 by a simple gift, a pocket compass. As the needle quivered and settled, pointing faithfully to an unseen pole, the boy grasped his first great lesson. The world was not just what you could see and touch. There was an invisible architecture operating behind the scenes, a set of pure, beautiful laws that governed movement without visible contact. He described this moment as his most profound experience, realizing that something deep hidden had to be the source of all reality. This sense of awe for the unseen order became the driving engine of his life. This natural curiosity collided violently with the authoritarian culture of the late 19th century German gymnasium. The school demanded unquestioned obedience and rote learning, valuing discipline over genuine inquiry. For Einstein, who valued the truth above all else, this was intellectual torture. He later confessed that the school system was dedicated to killing the holy curiosity of inquiry. His rebellion against this system was not laziness. It was a philosophical defense of the intellect's autonomy. He found refuge only in the self-constructed world of pure thought. At 12, he encountered Euclidean geometry, and it became his sacred little book. Here, finally, was a system built entirely on logical necessity, where unshakable truth could be derived from simple axioms. He realized that the human mind, through reason, could build a more perfect reality than that offered by his senses. The collision between his private pursuit of truth and the public demand for conformity reached a head. Following the failure of his family's business and their move to Milan, Einstein made a series of defiant choices. He abandoned the German school and critically renounced his German citizenship. He chose to be stateless, to be a citizen of the world, free from the obligations of nationalism and militarism that he despised. His goal was the liberal, independent Swiss Federal Polytechnic School, ETH, in Zurich. His first attempt to enter, at age 16, failed. His brilliance in math and physics could not compensate for his disregard of other prescribed subjects. This temporary setback forced him to take a year for self-study and refinement, a necessary period that ultimately deepened his intellectual focus. He eventually entered the ETH in 1896, but his refusal to submit to uninspired teaching continued. He was a cut-class specialist, preferring the solitude of the library and laboratory to the dull lectures. His true education was a private war waged through the books of James Clerk Maxwell, the master of electromagnetism, whose work he independently mastered while his classmates followed the required syllabus. This intellectual insubordination cost him dearly. When he graduated in 1900, his alienated professors effectively blacklisted him from academia. He was left with no prospects, struggling through 2 years of humiliating, precarious work as a private tutor. The greatest mind of his generation was marginalized, forced into obscurity by the very institutions he was destined to save. His salvation, and the world's, arrived in 2 forms. First, Mileva Maric, the only woman in his class and his intellectual mirror. Their intense partnership, cemented by a shared skepticism of scientific authority, provided the crucial sounding board for his radical ideas about motion and fields. Second, the Swiss Patent Office in Bern. In 1902, he secured a position as a technical expert 3rd class. The irony was exquisite. The man who would dismantle the absolute laws of the universe was paid to review the mundane mechanics of new inventions. But this very mundanity became the perfect camouflage. The work analyzing electromagnetic patterns required a deep, analytical focus on the very mechanics he was questioning, but did not drain his spirit with academic politics. His mind was finally free to roam. At night, in the secrecy of his apartment, the Olympia Academy met. A handful of friends who devoured the skeptical philosophy of David Hume and Ernst Mach, questioning the very concepts of absolute time and absolute space upon which Newtonian physics stood. The single great contradiction of physics, the puzzle of the luminiferous ether, was his obsession. Experiments could not detect the ether, yet classical physics required it to carry light. The logical tension was intolerable to a mind trained in the absolute necessity of Euclidean geometry. The resolution came, as always, from his private world of thought. The famous Gedanken experiment. If I rode alongside a beam of light, what would I see? The answer, compelled by the laws of Maxwell, forced him to realize that the speed of light had to be absolute and constant for all observers. This single, simple truth shattered the established order. If the speed of light is constant, then time and space must be relative. They must bend and contract to maintain that universal speed limit. The 26-year-old patent clerk, working alone, had broken the chains of fixed time. With his 2 revolutionary postulates defined, the greatest intellectual explosion in history was primed. The year 1905 was about to begin, and a quiet series of papers, conceived in the silence of a bureaucrat's desk, was ready to remake the universe forever. The quiet years of obscurity were over. We now turn to the astonishing single year that historians call the Annus Mirabilis, the year the world first felt the power of Einstein's pen. The year of miracles, 1905, and the dawn of special relativity. The year is 1905. In the grand established universities of Europe, Berlin, Cambridge, Göttingen, esteemed professors were teaching the fixed, immutable laws of Isaac Newton, secure in the knowledge that they understood time, space, and motion. Yet in the quiet, methodical world of the Swiss Patent Office in Bern, a 26-year-old clerk was about to unleash 4 papers that would systematically shatter that secure foundation. This year, the Annus Mirabilis, the year of miracles, stands as the most explosive, concentrated burst of scientific genius in modern history. Einstein did not publish one revolutionary theory in 1905. He published 4, each deserving of a Nobel Prize, and each tackling a distinct, fundamental problem that had long frustrated the global scientific community. The sheer scope of his intellectual ambition, undertaken while analyzing industrial blueprints, is what truly defines this period. The First Blow, The Reality of Atoms, the first paper titled On the Motion of Small Particles, Suspended in Liquids at Rest Required by the Molecular Kinetic Theory of Heat, arrived in March. It addressed the strange, erratic jiggling of microscopic particles suspended in fluid, a phenomenon known as Brownian motion. This movement had been observed for decades, but no one had provided a definitive quantitative explanation. Einstein's genius was to connect this visible, chaotic motion directly to the invisible reality of atoms. He reasoned that the visible particles were being constantly randomly bombarded by the far smaller, unseen molecules of the fluid itself. He didn't just propose this, he provided a precise mathematical model to predict and measure the movement. This paper was a decisive, empirical proof of the existence of atoms and molecules, a concept still fiercely debated by many influential physicists and chemists at the time. This simple, elegant explanation suddenly made the atom real and measurable, forever silencing the skeptics and providing a critical foundation for modern chemistry and physics. It was a philosophical triumph, making the invisible visible through the power of mathematics. The Second Blow, Light as a Particle, the Photoelectric Effect, the second, and perhaps most philosophically daring paper, arrived in May. On a heuristic point of view concerning the production and transformation of light. This paper dealt with the photoelectric effect, the phenomenon where light shining on a metal surface causes electrons to be ejected. Classical physics, based on Maxwell's equations, treated light purely as a wave, a continuous oscillation in the mysterious ether. This wave theory, however, failed spectacularly to explain why the color, frequency of the light, not its intensity, brightness, determined whether electrons were ejected. Einstein's solution was audacious. He proposed that light, in its interaction with matter, must behave not as a continuous wave, but as a stream of discrete, tiny energy packets. He called these packets quanta, later named photons. This revolutionary idea that light exists in bundles marked the true beginning of quantum theory. It was a radical departure from the established wave model, suggesting that reality was fundamentally granular, not smooth. By proposing that energy existed in specific quantized steps, he had laid the groundwork for the most counterintuitive and philosophically challenging branch of physics. Crucially, this paper directly challenged the very nature of light itself, suggesting a wave-particle duality, a profound paradox that would perplex physicists for the next century. This was the work for which 16 years later, he would finally be awarded the Nobel Prize in Physics. The Third Blow, Special Relativity, The End of Absolute Time. The third paper, published in June, was the one that truly changed the universe, on the electrodynamics of moving bodies. It contained the special theory of relativity. This was the culmination of his years of solitary wrestling with the problem of the ether and the contradictions in classical electromagnetism. Einstein began not by building on Newtonian physics, but by demolishing its philosophical foundation, the idea of absolute space and absolute time. His theory rests on two simple yet revolutionary postulates: the principle of relativity. The laws of physics are the same for all observers moving at constant velocity. The constancy of the speed of light. The speed of light in a vacuum, Sicky's, is the same for all inertial observers, regardless of the motions of the light source. The second postulate, the idea that the speed of light is a universal speed limit and an unbreakable constant, forced the radical conclusion: if the measured speed of light must remain the same for every observer, then space and time must be flexible and relative. This meant that there is no absolute now in the universe. Time flows differently for objects in motion relative to one another. Time dilation. For an observer moving at high speed, time slows down relative to a stationary observer. Length contraction. Similarly, the length of an object appears to shrink in the direction of motion. Simultaneity is relative. Two events that appear simultaneous to one observer might occur sequentially to another. The theory was a masterpiece of logical necessity, conceived entirely from pure thought and these two axioms. It did not require new experiments. It only required a radical shift in perspective. The universe was no longer a stage upon which events unfolded. The stage itself was an active, flexible participant. The fourth blow, E=mc2, the most famous equation, the final paper, an addendum titled, "Does the inertia of a body depend upon its energy content?" arrived in September. Though seemingly modest, this paper delivered the most famous result of his entire career, a breathtaking simplification of the universe's profound relationship between matter and energy. It was in this paper that Einstein derived the stunning conclusion from special relativity. Mass and energy are not separate entities. They are two manifestations of the same thing. The tiny amount of mass, a cm, lost in a chemical or nuclear reaction, is converted into a colossal amount of energy, E, scaled by the square of the speed of light, c2 E nars or mc2. This equation revealed the immense energy locked within every gram of matter. It explained the power source of the stars and provided the theoretical basis, decades later, for atomic energy. Philosophically, it completed the synthesis, proving that the seemingly solid, tangible world of mass was merely a form of highly concentrated energy, the quiet aftermath and the struggle for recognition. The immediate reception to this outpouring of genius was not one of global acclaim, but one of confused silence. Remember the context. The author of these 4 revolutionary papers was a low-level patent clerk who held no academic post, no PhD. He was only in the process of submitting his dissertation, and published his work in the Annalen der Physik with no institutional affiliation. The scientific community initially struggled to take the anonymous source seriously. The papers were received with a mixture of skepticism and neglect. For months, the only prominent physicist who recognized the profound significance of the work was Max Planck, the founder of quantum theory and a figure of great authority in Berlin. Planck immediately recognized the genius of the special relativity paper and began to champion the work, assigning his students to study it. Einstein, meanwhile, continued his life in Bern. He was promoted to technical expert second class at the patent office in 1906, a modest bureaucratic gain that showed his employers appreciated his diligence, completely oblivious to the fact that he had just rewritten the laws of the cosmos on their payroll. His domestic life remained complex. While the intellectual excitement with Mileva was immense, the financial anxieties and the responsibilities of fatherhood, his son Hans Albert was born in 1904, were constants. He was forced to continue his dual life, the meticulous bureaucrat by day, the cosmic architect by night. The academic world slowly and reluctantly, began to take notice in the years immediately following 1905. The evidence for the quantum nature of light and the mathematical necessity of relativity began to accumulate, making it impossible to ignore the claims of the clerk from Bern. In 1908, a major turning point, he finally received his first academic recognition when he was appointed as a private docent, an unsalaried lecturer at the University of Bern. This position was symbolic rather than financial, forcing him to lecture in his spare time and receive no pay, but it was his first step back into the academic world. The long struggle for a proper academic position finally ended in 1909, 4 years after the Annus Mirabilis, when he secured his first salaried, tenure-track position as an associate professor of theoretical physics at the University of Zurich. He was finally free of the patent office, but the years of obscure, intense intellectual labor had already shaped his unique approach. He had learned to trust his own, unconstrained thought above all external authority. But special relativity was only the beginning. It dealt only with observers moving at constant velocity. The entire universe, however, is a place of accelerating, curving, and massive objects. To fully integrate gravity into his new theory of space-time, Einstein knew he had to embark on a far more demanding 10-year intellectual war, a struggle that would test the very limits of his mathematical and physical intuition, leading him to the concept of general relativity and the full geometry of the universe. The 10-year war, gravity as geometry, and the agony of general relativity. The victory of special relativity in 1905 was a masterpiece of logical construction. It provided a perfect framework for motion at constant speeds and proved that time and space were flexible. Yet, as Einstein himself knew, it was a theory for a universe that did not exist, a universe without mass, acceleration, or the crushing reality of gravity. The real cosmos, the one filled with accelerating planets, massive stars, and immense curvatures, required a far deeper theory. The task of integrating gravity into his new flexible framework became the consuming intellectual war of the next decade, a brutal, exhausting campaign fought primarily in the solitude of his mind, stretching his genius to its absolute breaking point. The price of genius, marriage, and movement. The year immediately following the Annus Mirabilis were a period of intense professional ascent, but escalating personal turmoil. Einstein transitioned rapidly through Europe's top academic posts, from the University of Zurich to the German University in Prague, and then back to the prestigious ETH in Zurich. Each move brought greater recognition, but this constant upheaval was devastating to his wife, Mileva Maric, and their young sons, Hans Albert and Eduard. Einstein became increasingly absorbed by the abstract problem of gravity, seeing his personal life as a secondary distraction from his cosmic quest. The intense intellectual bond that had sustained their marriage through the lean years in Bern began to unravel under the pressure of his growing fame and his emotional distance. The ultimate fracture occurred with the move to Berlin in 1914. Einstein accepted the most coveted research position in the German Empire, a directorship at the Kaiser Wilhelm Society and a professorship at the University of Berlin with no required teaching duties. This was intellectual freedom, but Mileva found the city isolating and hostile. They separated, and she returned to Zurich with their children. The divorce was painful and marked by Einstein's promise to give her the financial proceeds of the Nobel Prize, a striking testament to his deep, unwavering conviction that the ultimate validation of his work was only a matter of time. 2. The happiest thought, gravity as acceleration. The genesis of his new theory, general relativity, came from a single, simple realization in 1907 that he later described as the happiest thought of my life. He imagined a man falling freely from a great height. In that brief moment of free fall, the man would feel weightless. If he released any object, it would appear to float beside him. Einstein realized that in that moment, the effects of gravity had completely vanished. This led him to the principle of equivalence. A person in a sealed environment cannot distinguish between being pulled down by gravity and being pushed up by acceleration. The two effects are perfectly fundamentally interchangeable. This idea shattered the Newtonian view of gravity as an invisible, attractive force. If gravity is equivalent to acceleration, then gravity must be an inertial effect, a consequence of motion within a warped field, not a mystical pull. The third, the fatal flaw of absolute space and time. Einstein saw that his previous theory, special relativity, could not handle this idea. Special relativity was based on inertial frames, objects moving at constant, unaccelerated velocity. But since gravity is acceleration, a complete theory had to solve physics for all possible motions, including those that are accelerating and curving. Furthermore, Newton's theory stated that the gravitational influence of a mass, like the sun, was felt instantaneously across space. This was now logically impossible, because special relativity had established the speed of light as the absolute, universal speed limit. Gravity, too, must travel at a finite speed. This meant that the sun's influence could not be a force acting across space. It had to be a feature of space itself. The desperate need for new math. The challenge was not conceptual, it was mathematical. Einstein's revolutionary idea that gravity warps the structure of the cosmos required a mathematics far more complex than the simple algebra of special relativity. He needed a way to measure distances and curves on surfaces that were not flat but continuously changing. He was initially stumped, admitting his own mathematical limitations. His rescue came from his trusted friend and former classmate from the ETH, Marcel Grossmann, now a professor of mathematics. Grossmann introduced Einstein to the incredibly difficult field of non-Euclidean geometry, specifically tensor calculus, or Riemannian geometry. This was the sophisticated esoteric language needed to describe curvature in 4 dimensions, the 3 dimensions of space plus the dimension of time. Grossmann taught Einstein this daunting mathematical language, becoming his crucial partner in the long, arduous process of translating his physical vision into a precise, self-consistent geometry. The collaboration was a testament to the power of intellectual friendship. V-gravity as the geometry of spacetime. The core realization of general relativity was profound and simple. Gravity is not a force, it is the physical geometry of spacetime. Einstein proposed that mass, such as a star or a planet, does not pull on objects. Instead, it warps the fabric of spacetime around it, much like a heavy bowling ball placed on a stretched rubber sheet causes an indentation. When a planet or a beam of light travels near this massive object, it is not being tugged. It is simply following the straightest possible path, a geodesic, in the curved region. What we perceive as the force of gravity is actually just motion along the topography of the cosmos. This meant that the stage of the universe was no longer passive. It was an active, dynamical participant in every physical event. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. 6. The final race in wartime Berlin, 1915. The final year of creation was marked by relentless intellectual pressure. Einstein was working in the shadow of war and under the immediate threat of a mathematical rival, the great German mathematician David Hilbert, who was also close to discovering the correct equations. This competition spurred Einstein into a desperate, feverish final push. In November 1915, isolated in wartime Berlin, Einstein worked with incredible intensity, publishing a series of weekly communications, correcting previous errors, and refining the mathematics. Finally, in the last week of November, he presented the complete and correct set of field equations of general relativity to the Prussian Academy of Sciences. These equations, though incredibly complex, were the mathematical expression of his vision. They described the exact relationship between the curvature of spacetime and the distribution of matter and energy within it. 7th, the proofs, new predictions for a curved universe. A new theory must do more than just explain what is known. It must make new, verifiable predictions. General relativity made 3 stunning predictions that deviated measurably from Newtonian mechanics. The precession of Mercury's orbit. General relativity predicted that the planet Mercury's orbit should slowly rotate around the Sun by a tiny specific amount, an extra 43 arcseconds per century. This was a known anomaly that had puzzled astronomers for decades, and Einstein's equations perfectly accounted for it. This precise explanation was the first powerful confirmation of the theory. The bending of starlight. The most dramatic prediction was that light, traveling from distant stars and passing close to the massive gravity well of the Sun, would be bent by the Sun's warped spacetime. The angle of this deflection was predicted to be exactly twice the amount that Newton's simpler calculation suggested. This required a measurement that could only be taken during a total solar eclipse, when the Sun's intense light is completely blocked, allowing the background stars to be photographed. Gravitational redshift and time. The theory also predicted that light escaping from a strong gravitational field would lose energy, causing its wavelength to lengthen, shift to the red end of the spectrum. More profoundly, this effect implied that time runs slower in stronger gravitational fields. The passage of time itself is relative to the geometry surrounding it. The agonizing period of pure creation was now complete. The theory was a masterpiece of physics and geometry, but it remained a theoretical claim until it could be proven against the harshest reality, the stars themselves. The scientific community, though reeling from the complexity of the math, demanded proof. The fate of general relativity now rested entirely on an event that was quite literally out of this world. The light that bent, eclipse, fame, and the curved universe. The year 1915 had seen the birth of general relativity in the solitude of wartime Berlin, a triumph of pure thought and complex mathematics. But the theory remained an abstract claim, a beautiful set of equations locked in a physics journal. The only way to prove that the universe was truly a place of curved, flexible geometry rather than a fixed Newtonian stage was to test its most audacious prediction, that the immense mass of the Sun would visibly bend the light of distant stars as it passed close by. This experiment required a total solar eclipse, an event where the moon perfectly blocks the sun, allowing the faint light of background stars to be photographed right next to the sun's fiery corona. I, the war, and the scientific isolation. The years between 1915 and 1919 were dominated by the catastrophic violence of World War I. Germany, where Einstein worked, was isolated from the Allied nations. This isolation cut Einstein off from the global scientific community, making international collaboration, and therefore the necessary eclipse expedition, impossible for years. Paradoxically, Einstein used the war years not for patriotic endeavors, but for a profound dedication to pacifism and internationalism. As a German resident who held Swiss citizenship, he openly opposed the militarism of the Prussian Academy, often finding himself isolated even within his own city. He believed that the laws of nature and the quest for truth transcended all national and political boundaries, maintaining quiet contact with colleagues across borders. Unrekun, the quiet champion, was Arthur Eddington. The task of testing general relativity fell to a man of profound courage and conviction, Sir Arthur Stanley Eddington, a leading British astrophysicist and a devout Quaker. Eddington was intrigued by the mathematical elegance of general relativity, and crucially, by Einstein's principled pacifism. In a world torn apart by nationalism, Eddington saw the test of general relativity as a transcendent human act, a chance to prove that reason and scientific cooperation could bridge the bitter divide between warring nations. Eddington possessed the necessary authority and skill to launch the ambitious expeditions. He was also a rarity, one of the few people in the world who truly understood the dense, complex mathematics of general relativity. The third, the 1919 expedition across the globe. In 1919, shortly after the war's conclusion, Eddington seized the opportunity presented by a total solar eclipse scheduled for May 29th. The path of totality was ideal, crossing the South Atlantic. Two separate expeditions were organized to ensure success and redundancy. Principe Island, a small, remote island off the coast of West Africa, led by Eddington himself. Sobral, Brazil, a site in South America, led by Andrew Crommelin. The conditions were far from ideal. Both teams faced immense logistical challenges, difficult weather, thick jungle humidity, and in Eddington's case on Principe, a complete cloud cover that threatened to ruin the entire experiment. During the critical minutes of totality, Eddington managed to take a series of photographs. Most were blurred or rendered useless by the weather, but one plate 16, showed multiple background stars clearly visible around the eclipsed sun. The same was true for the plates taken in Sobral. A 4, the measurement and the verdict. The essence of the experiment lay in measuring the apparent shift in the positions of the background stars. Stars whose light passed close to the sun's immense mass should appear slightly displaced from their known positions due to the light being bent by the curved spacetime. Newton's theory, treating lights only as mass influenced by gravity, predicted a very small bending angle. Einstein's general relativity, treating gravity as the warping of spacetime, predicted an angle exactly twice the Newtonian value. Back in England, Eddington meticulously compared the eclipse photographs with control photographs of the same star field taken months earlier when the sun was elsewhere. The results were conclusive. The light had been bent by the predicted amount, the Einsteinian value. The verdict was unambiguous. Newton was wrong. Space was curved. V, the announcement, and the global earthquake. The official announcement of the results was made at a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6, 1919. The atmosphere was electric. Sir J.J. Thomson, the president of the Royal Society, declared that the findings were a most important result of human thought and represented the greatest discovery in connection with gravity since Newton. The following day, November 7th, 1919, the headline in the Times of London read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." This marked a cultural moment unlike any other in scientific history. The announcement was picked up by newspapers across the globe, instantly transforming Albert Einstein, the quiet, middle-aged, politically controversial German professor, into a scientific deity and the world's first celebrity scientist. 6. The philosophical shockwave. The public fascination went far beyond the astronomical data. The profound philosophical implications of general relativity delivered a shockwave to the cultural consciousness of the post-war world. The theory confirmed that absolutes were illusions. If space and time, the most foundational concepts of reality, were flexible, relative, and dependent on motion and mass, what other certainties could be trusted? The public, weary of the war's chaos and the collapse of traditional moral and political structures, found in Einstein's curved universe a strange, almost unsettling echo of their own experience. His theory seemed to legitimize the idea that everything was relative, despite Einstein's own insistence that his theory was built on the absolute constant of the speed of light. His personal style only fueled the fire. His shaggy hair, modest attire, deeply human eyes, and soft-spoken demeanor stood in sharp contrast to the rigid, formal scientists of the previous generation. He became the icon of the independent thinker, a man who overthrew a giant like Newton using nothing but pure thought. 6th, the burden of celebrity. The sudden transition from obscurity to global fame was deeply jarring for Einstein. He became one of the most recognized and sought-after individuals on the planet, constantly besieged by reporters, photographers, and letter writers seeking his philosophical, political, or scientific opinion on every subject. He hated the fanfare and the relentless intrusion into his private, contemplative life. He often spoke of his longing for solitude, viewing fame as an unnecessary burden that interfered with the one activity he truly cherished, thought. He famously referred to himself as a solitary traveler who had accidentally found himself on the world's stage. However, he learned to leverage his fame for two crucial causes: pacifism. He used his voice to tirelessly advocate for world peace and international cooperation, remaining committed to his anti-militarist principles that had isolated him during the war. Zionism. As an influential secular Jew, he became a public face for the Zionist movement, raising funds and advocating for the establishment of a Jewish homeland, connecting his personal identity to a global political cause. 8. Consolidating the new physics. Despite the chaos of celebrity, Einstein's academic position was now unassailable. He was awarded the Nobel Prize in Physics in 1921, though significantly, the prize citation specifically mentioned his work on the photoelectric effect from 1905, and only diplomatically referenced his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. The Nobel Committee, wary of the philosophical and political controversy surrounding general relativity and quantum theory, chose to honor the most empirically settled of his revolutionary papers. As promised, the prize money was immediately transferred to his ex-wife, Mileva. With the fundamental architecture of the universe settled, space-time was curved, light was quantized, and mass was energy, Einstein's focus shifted again. He became increasingly preoccupied with the strange, unsettling nature of quantum mechanics, the very field he had helped to launch with his light quantum paper. The universe, it seemed, was not just curved, it was also fundamentally random and probabilistic, a concept that deeply offended his lifelong search for pure, logical order. God does not play dice, the quantum war, and the search for unity. The year 1919 vaulted Einstein to global fame, but the triumph of general relativity marked the end of his profound contribution to the established structure of physics. His remaining decades would be defined not by revolutionary success, but by a tenacious, deeply philosophical rearguard action against a field he had inadvertently helped to launch: quantum mechanics. This was the greatest intellectual conflict of his life, a struggle not against other physicists, but against the very nature of randomness that the universe seemed to insist upon. The unsettling legacy of the photon. The irony was profound. Einstein's 1905 paper on the photoelectric effect, the very paper that won him the Nobel Prize, had introduced the concept of the light quantum, photon, suggesting that energy was delivered in discrete, tiny packets. This idea directly challenged the classical view of light as a continuous wave and laid the foundation for the entire quantum revolution. By the mid-1920s, the new generation of physicists, Niels Bohr, Werner Heisenberg, Max Born, and Erwin Schrödinger, had developed quantum theory into a full, coherent, albeit bewildering model of atomic reality. This model held that the world at the subatomic level is inherently probabilistic. We can only predict the likelihood of an electron being in a certain location, not its certain position. The act of observation fundamentally changes the state of the observed particle, Heisenberg's uncertainty principle. Particles exist in a superposition of states until measured, Bohr's Copenhagen interpretation. For Einstein, a man who had dedicated his life to uncovering the pure, necessary, and deterministic laws of the universe, this probabilistic view was a philosophical atrocity. 2. The deterministic heart Einstein's entire philosophical approach, inherited from Spinoza and Kant, was rooted in determinism. He believed in a universe governed by causal laws, where every effect has a precise, knowable cause. The idea that God, or the universe's ultimate mechanism, would rely on random chance was intolerable. This conviction was famously summarized in his most quoted philosophical declaration regarding quantum mechanics. God does not play dice with the universe. His disagreement was not merely technical, it was a metaphysical rejection of the notion that fundamental reality could be based on chance. He believed that the quantum description was incomplete, and that beneath the observable randomness lay hidden variables, deeper, deterministic laws yet to be discovered. The third, the Bohr-Einstein debates, the great intellectual duel, the conflict between Einstein's deterministic worldview and the quantum mechanical view came to a head in a series of legendary intellectual duels, primarily held at the Solvay conferences in the late 1920s and 1930s, between Einstein and his great friend and rival Niels Bohr. These debates were respectful, profound, and often witty, but they represented the deepest schism in modern physics. Einstein's strategy. Einstein would devise ingenious Gedanken thought experiments, designed to expose logical flaws or contradictions in the uncertainty principle or the Copenhagen interpretation. He sought to prove that a particle's position and momentum could be simultaneously known, thereby rendering the quantum theory inconsistent. Bohr's defense. Bohr, acting as the philosophical defender of quantum mechanics, would patiently dismantle each of Einstein's logical challenges, often using the very principles of general or special relativity to show that Einstein's proposed experimental setup was impossible. Bohr invariably demonstrated that the apparatus required to measure one property precisely would inherently disturb the other, preserving the uncertainty principle. These debates established Bohr as the philosophical victor in the eyes of the younger generation. Einstein, though admired, became increasingly isolated from the mainstream of physics, clinging stubbornly to his belief in a complete causal reality. A fool. The EPR paradox, a final attempt to tame the chaos. Einstein's final, most powerful challenge to quantum mechanics came in 1935 with the publication of a paper co-authored with his young colleagues Boris Podolsky and Nathan Rosen, known as the EPR paradox. The paper proposed a thought experiment involving two quantum particles that interact and then fly apart. Due to the rules of quantum entanglement, measuring a property of the first particle, say its momentum, instantly tells you the corresponding property of the second particle, even if the particles are light years apart. Einstein argued that since the measurement of the second particle was performed without any physical interaction, its properties must have been real and deterministic all along. Otherwise, the influence would have to travel faster than the speed of light, a phenomenon he famously called spooky action at a distance. For Einstein, this meant one of two things. Either quantum mechanics allowed faster than light communication, violating relativity, or more likely, quantum mechanics was an incomplete theory. It failed to describe the real, deterministic state of the universe. Though largely ignored by the mainstream at the time, the EPR paradox introduced the concept of quantum entanglement and became the foundational text for modern quantum information theory, ironically providing the theoretical basis for new fields like quantum computing. V. The decades-long quest for a unified field theory. From the late 1920s until his death in 1955, Einstein committed himself almost entirely to one final, gargantuan project, the search for a unified field theory, UFT. Having successfully unified space and time, and mass and energy, he believed the ultimate goal of physics was to find a single, elegant set of equations that could describe all fundamental forces of the universe as manifestations of the same geometric field. Specifically, he sought to unify his own theory of gravity, general relativity, with the theory of electromagnetism, hoping to eliminate the probabilistic chaos of quantum mechanics in the process. This was a profoundly ambitious goal, a return to the initial childhood dream of finding the hidden architecture behind all things. The approach. Einstein believed that the universe could be described by a single, classical deterministic field. He worked primarily with advanced classical field theory, attempting to expand the geometry of general relativity to include electromagnetism. The isolation. This quest ultimately led to his profound scientific isolation. While the rest of the physics community focused on building the quantum theory, which became the basis for modern particle physics, Einstein pursued a path that many considered a dead end, a beautiful but ultimately unattainable classical dream. His mathematical efforts became increasingly esoteric and detached from experimental reality. He was searching for the philosophical cornerstone he believed was missing: causality and determinism. He became a symbol of the lone scientific prophet, unwilling to compromise his deep-seated conviction in the rationality of the universe. Sixth, the gathering storm, fascism and emigration. While immersed in this cosmic quest, the political reality of Germany was deteriorating rapidly. The rise of Nazism brought with it virulent anti-Semitism, and Einstein, a prominent Jewish voice and an avowed pacifist, became a prime target. In 1933, while on a lecture tour abroad, Adolf Hitler came to power. Recognizing the immediate and existential threat, Einstein made the defining choice of his political life. He would not return to Germany. The Nazi regime immediately seized his property, revoked his German citizenship, and publicly condemned his work as Jewish science. The quiet professor, who had once been the pride of Germany, was now its most famous intellectual enemy. This sudden, forced emigration transformed his personal and professional life entirely. He needed a new, permanent home, and the search for scientific truth became inextricably linked with the search for safety and freedom. The ultimate destination for this self-proclaimed solitary traveler would be the New World, the United States, where his greatest political challenge still awaited him. The New World and the Nuclear Shadow. EOSMC2 confronts the state. The year 1933 marked the profound shift in the life of Albert Einstein, severing his ties to European academia and forcing his entry onto the American stage. Fleeing the toxic rise of Nazism, his journey from the intellectual pinnacle of Berlin to the quiet suburbs of New Jersey symbolized the tragic migration of European genius under the shadow of totalitarianism. His arrival in the United States brought him sanctuary, but it also forced him to confront the terrible, unforeseen military power latent within his abstract equations. The sanctuary of Princeton, the immediate, essential need for safety, led Einstein to accept a permanent position at the newly established Institute for Advanced Study, IAS, in Princeton, New Jersey. This institution was designed as a haven for the world's greatest scholars, free from the administrative burdens of teaching and academic politics, allowing them to focus entirely on fundamental theoretical research. For the remainder of his life, Princeton would be his home. He found the atmosphere, the quiet campus, the surrounding streets, and the philosophical freedom a welcome change from the fraught political climate of Germany. He quickly became one of the most visible and respected residents of the town, known for his signature look: the ever-present uncombed hair, the simple sweater, and the refusal to wear socks. He often walked home, deep in thought, an icon of pure, unburdened contemplation. His second wife, Elsa Lowenthal, whom he had married in 1919, provided the necessary domestic stability, managing the logistics of his famous life. After her death in 1936, Einstein retreated further into his work and his cherished solitude, surrounded only by his stepdaughter and his personal secretary. The continuation of the unified quest, even in America, Einstein's professional focus remained singular and intensely philosophical. The search for the unified field theory, UFT, while the rest of the physics community, primarily in the United States and Europe, continued to build upon the probabilistic foundations of quantum mechanics, a science that would soon unlock the power of the nucleus, Einstein remained firmly committed to his final, great, and increasingly isolated quest. He believed, as he had since childhood, that the universe was a structure of logical necessity and order. He spent decades attempting to expand the geometrical elegance of general relativity to encompass the forces of electromagnetism, believing that the entire cosmos at its root was a single, classical, deterministic field. This dedication to classical determinism, however beautiful, meant he was intellectually detached from the experimental and theoretical breakthroughs that were happening around him in nuclear physics. The whisper of fission and the threat of Nazism, the world of physics was about to explode, literally, not through Einstein's theoretical geometry, but through the mechanics of the atom. In late 1938, just before the outbreak of World War II, German chemists Otto Hahn and Fritz Strassmann achieved the unthinkable. They successfully split the uranium atom. This process, nuclear fission, released an astonishing amount of energy and, crucially, released additional neutrons, suggesting the terrifying possibility of a self-sustaining chain reaction. The news of this breakthrough immediately traveled across the Atlantic, carried by émigré scientists who understood its immense world-changing implications. They recognized the horrific potential. If a chain reaction could be controlled in a large mass of uranium, the result would be an explosion of unparalleled destructive power, an atomic bomb. The fear was primal. Germany had done the initial work, and a Nazi regime armed with such a weapon would be unstoppable. The letter to Roosevelt, the moral imperative. Though politically active as a pacifist and humanitarian, Einstein was not involved in the practical world of nuclear physics. However, his name held unmatched moral and scientific weight. In the summer of 1939, shortly before the war began, the Hungarian physicist Leo Szilard, along with Eugene Wigner and Edward Teller, recognized that they needed to alert the American government at the highest level. They needed to use a name that would command immediate attention. Szilard drafted a letter detailing the potential for a chain reaction using uranium and warning that the German government was actively supporting research into this area. He then drove to Einstein's summer home on Long Island. Einstein, initially unaware of the detailed mechanics of the chain reaction, immediately grasped the moral and political imperative of the situation. He recognized that his pacifism in this unique circumstance had to yield to the existential threat posed by Hitler's regime. On August 6, 1939, Albert Einstein signed the Einstein-Szilard letter, addressed directly to President Franklin D. Roosevelt. The letter urged the president to establish a dedicated, large-scale American research program into the potential of uranium as a new, powerful weapon. The unintended father of the atomic age, the letter, more than any other single factor, was the catalyst that spurred the American government to dedicate serious resources to nuclear research. It eventually led to the creation of the secret, massive scientific undertaking known as the Manhattan Project. The irony was profound and tragic. The formula that began the entire scientific inquiry was Einstein's simple, elegant realization from 1905. Excuse the dollars, energy equals mass times the speed of light squared. This equation revealed the immense energy locked within matter, and it was now being used as the blueprint for planetary destruction. Einstein, the lifelong pacifist, had unwittingly played the pivotal role in starting the arms race for the ultimate weapon. The isolation from the project. Despite his initiating role, Einstein was never asked to participate in the Manhattan Project itself. His history as an open socialist and a radical pacifist, combined with his long record of anti-nationalist statements, made him a high-risk security liability in the eyes of the FBI and U.S. military intelligence. The U.S. government knew the risks of his political convictions and kept the world's greatest theoretical physicist far away from the practical work of building the bomb. He continued his life at Princeton, immersed in his UFT quest, while the terrifying practical application of his earlier work unfolded in secret laboratories across the continent, Hiroshima, and the profound regret. The true horror arrived in August 1945 with the dropping of the atomic bombs on Hiroshima and Nagasaki. The news of the successful detonation and the catastrophic destruction filled Einstein with profound remorse and moral agony. He had witnessed the abstract elegance of his life's work weaponized into mass murder. His primary feeling was one of overwhelming responsibility, despite his non-involvement in the project itself. He famously stated later in life, "Had I known that the Germans would not succeed in developing an atomic bomb, I would have done nothing for the bomb." This reflected his original limited goal, to neutralize the existential threat of a Nazi bomb, not to unleash a new era of global annihilation. The post-war years saw Einstein shift his focus almost entirely to political activism and humanitarian causes. He used his unparalleled fame, his immense moral authority, to campaign relentlessly for nuclear disarmament, the establishment of world government, and the peaceful control of atomic energy. The solitary architect of the cosmos became the world's most visible scientific activist, burdened by the terrible moral weight of his own earlier discovery. His final decades were a relentless attempt to find a political solution that could match the technological power he had unleashed, proving that the deepest truths of the universe often come with the heaviest ethical responsibility. The Solitary Voyager. Final years, philosophy, and the enduring light by the late 1940s, Albert Einstein had fully transitioned from scientist to moral authority. The man who had been the architect of the cosmos was now consumed by the terrifying political and moral implications of his own creations. His final years, spent in the quiet intellectual sanctuary of the Institute for Advanced Study in Princeton, were a continuous effort to reconcile the beautiful, deterministic order he saw in nature with the violent, chaotic reality of human affairs. The sage of Princeton, a public icon in his last decade, Einstein became the visual and ethical embodiment of the wise scientist. His iconic image, the halo of uncombed white hair, the deep, sorrowful eyes, the simple clothes, made him instantly recognizable and infinitely marketable. He was frequently stopped on the streets of Princeton by students, children, and visitors, seeking simple answers to complex questions, or merely a glimpse of the man who had bent light. He was often asked to explain relativity in a sentence, a task he generally greeted with self-deprecating humor. When asked about his scientific method, he never spoke of labs or equipment. He spoke of the power of pure thought and the importance of imagination which he considered more important than knowledge. His house on Mercer Street became a site of quiet pilgrimage, yet he successfully maintained his intellectual rhythm. He continued to walk the short distance to the Institute daily, often with his head bent in contemplation, carrying a lifetime of scientific weight with a gentle, almost childlike humility. The enduring quest for unity. Throughout these years, his primary intellectual focus remained fixed on the elusive unified field theory, UFT. He worked tirelessly, filling notebooks with complex mathematical attempts to integrate general relativity and electromagnetism into a single, cohesive geometry. He was well aware that the rest of the physics community had moved on, embracing the probabilistic chaos of quantum mechanics and turning toward experimental particle physics. Einstein, however, could not yield his philosophical belief in a rational, deterministic universe. He sought not just a physical theory, but a philosophical completion, the ultimate confirmation that the universe was a place of ordered logic. This quest led to his final, complete scientific isolation. He recognized the irony, famously noting that he had become a fossil in his own time, admired for his past glories, but disregarded for his current research. Yet he continued, driven not by the need for validation, but by his profound, unshakable belief that the quantum description was merely a temporary scaffolding, hiding a deeper, more elegant truth. The moral voice, pacifism, and civil rights, freed from academic politics and burdened by the nuclear legacy, Einstein dedicated his moral authority to two critical fronts: global peace and social justice. Nuclear disarmament. He became the world's most prominent advocate for nuclear disarmament and the establishment of a world government, arguing that the age of the atomic bomb had rendered the concept of absolute national sovereignty obsolete. He believed the only way humanity could survive the power of atomic $2 was through a radical political transformation towards a unified global authority. Civil rights. Shocked by the pervasive racial segregation and discrimination he witnessed in the United States, Einstein became an outspoken champion of the civil rights movement. He joined the NAACP, corresponded with prominent African American scholars, and spoke publicly against racism, calling it the worst disease of American society. His support was rooted in his lifelong commitment to humanitarian principles and his own experiences as a victim of prejudice in Nazi Germany. In these efforts, his fame served its best purpose, lending immense moral weight to causes that often lacked high-profile white support. The nature of belief. Einstein's God, Einstein, was frequently pressed on his religious beliefs, a question that fascinated the public, who desperately sought spiritual comfort from the man who understood the cosmos. He consistently rejected the notion of a personal God, a deity who intervenes in human affairs, rewards and punishes, or acts as a subjective moral authority. Instead, his belief was rooted in a profound sense of awe for the rational, necessary order of the universe. He subscribed to the God of the 17th century philosopher Baruch Spinoza, a pantheistic God identifiable with the impersonal, beautiful laws of nature itself. He defined his spiritual view as cosmic religious feeling, a sense of rapturous wonder at the elegance and structure of the universe, which he saw as a manifestation of superior reason. This belief fueled his science, confirming his conviction that the laws of physics were comprehensible to the human mind. His pursuit of the UFT was, in its deepest sense, a religious quest for the face of Spinoza's God. The Last Project, the State of Israel in 1952, following the death of its first president, Chaim Weizmann, Albert Einstein was offered the largely ceremonial position of president of the newly established State of Israel. It was an extraordinary honor, the offer of a political leadership role to a scientist and pacifist. Einstein respectfully declined the offer. He cited his lack of the necessary administrative skills, his advanced age, and his profound commitment to his scientific solitude. He preferred to serve the state through his moral voice and humanitarian support, rather than through political office. He remained, however, a devoted supporter of Israel and the Jewish people, seeing the state as a necessary bulwark against the threat of renewed persecution. The final hours. In early April 1955, Einstein experienced a rupture of an abdominal aortic aneurysm, a condition that had been monitored for years. He was taken to Princeton Hospital. Despite the pain, he remained lucid and calm. He requested his notebooks and the latest calculations concerning his unified field theory be brought to his hospital room. The doctors advised surgery, but Einstein, who possessed a profound philosophical resignation toward his own mortality, refused. He felt he had lived his life and did not wish to prolong it artificially. He famously stated, "I want to go when I want to go. It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it, and elegantly." He spent his final hours trying to solve one last equation, wrestling with the mathematical form of his UFT. Albert Einstein died quietly in his sleep in the early morning hours of April 18, 1955, at the age of 76. In accordance with his wishes, his body was cremated immediately without a public ceremony or gravesite, ensuring that his final resting place would not become an object of worship or pilgrimage. He maintained his commitment to intellectual humility, even in death, preferring that the focus remain on the ideas, not the man. The one striking act that violated his wishes occurred during the autopsy, when the pathologist, Thomas Harvey, removed Einstein's brain without permission, intending to study the physical source of his immense genius, an ironic, final intrusion into the solitude he had so fiercely protected. The scattered ashes were later dispersed in a secret, undisclosed location, returning the solitary voyager to the anonymity of the universe he had spent his life so beautifully revealing. Echoes of Geometry, The Legacy in the Cosmos, and the GPS. Albert Einstein concluded his life feeling that his grand design, the general theory of relativity, was incomplete, lacking the final piece that would unify it with the strange, chaotic world of the quantum. Yet the decades that followed his death revealed the immense, unimaginable scope of his mind. His geometry, born of pure thought and quiet contemplation, provided the cosmic blueprint for a universe far more active, dynamic, and dramatic than anyone, even he, had fully realized. His genius did not just reshape the distant stars, it quietly began to operate within the most mundane, necessary technology of our modern lives. The prophecy of expansion. When Einstein finalized general relativity in 1915, the scientific consensus was simple. The universe was a static, fixed volume of stars that had always existed and would always exist in the same relative scale. However, Einstein's own beautiful new geometric equations stubbornly resisted this idea. They naturally suggested that the universe must be either inflating or shrinking. To force his equations To agree with the static reality believed by his colleagues, he artificially inserted an extra mathematical term, a kind of counterweight, into his calculations. He later referred to this correction as the greatest blunder of his life, Hubble's confirmation. In the late 1920s, the American astronomer Edwin Hubble began observing distant galaxies. His data revealed a startling truth. All galaxies were racing away from us, and the farther away they were, the faster their recession. The universe was, in fact, demonstrably expanding. The rectified truth. When Einstein learned of Hubble's observational proof, he immediately discarded his artificial mathematical correction. He recognized that his original, unadulterated equations had correctly predicted the expansion of the universe years before any telescope had confirmed it. This was a stunning validation of the power of mathematical theory to reveal hidden truths about reality, demonstrating that pure thought could outpace physical observation. 2. The ultimate origin and the geometry of the Big Bang. The concept of an expanding universe led directly to the profound idea of the Big Bang. If everything is currently moving outward, tracing history backward must lead to a single, unimaginably dense, hot moment of origin. General relativity provides the crucial mathematical language for this entire cosmological framework. It describes how the geometry of the cosmos must evolve, defining the exact relationship between the density of all matter and the rate at which space itself stretches. The very beginning of the universe, its origin in time, is a concept directly derived from the flexibility of Einstein's curved spacetime. 3. The prediction of cosmic bottomless pits. Perhaps the most astonishing and unsettling consequence of general relativity is the prediction of black holes. The mathematical reality. Just weeks after Einstein published his field equations, a German physicist named Karl Schwarzschild found a perfect mathematical solution that described what happens when an enormous quantity of mass is concentrated into an incredibly small region of space, the event horizon. Schwarzschild's math predicted a boundary, the event horizon, where the curvature of spacetime is so steep that the force of gravity is inescapable. Within this boundary, nothing, not even light, can travel fast enough to escape the pull. This region, the black hole, is the ultimate physical manifestation of curved geometry, Einstein's discomfort. Ironically, Einstein remained deeply skeptical of black holes. He believed that the universe would somehow protect itself from such a catastrophic collapse, resisting the formation of such perfect cosmic traps. Yet modern astronomy has confirmed their existence beyond any doubt, showing that these objects, born from the death of massive stars, are a common and essential part of galactic structure. 4. Ripples in the fabric of space. General relativity treats space-time not as an empty void, but as a physical, pliable fabric. Just as throwing a stone into a still pond creates ripples on the surface, the theory predicted that the sudden, violent acceleration of massive objects, like two black holes spinning toward each other and colliding, should create ripples in the fabric of space-time itself. These ripples are called gravitational waves. Einstein predicted their existence, but the effect they generate is incredibly subtle. He doubted that humanity would ever possess the technology precise enough to detect them directly. It took a century, but in 2015, the LIGO collaboration finally achieved the first direct detection of gravitational waves, capturing the faint echo of a colossal collision that occurred over 1 billion years ago. This discovery was a profound victory for Einstein's geometry, opening up a completely new way to hear the cosmos through the vibrations of space itself, via relativity in your pocket, the GPS system. The most ubiquitous and essential application of general relativity is found not in the distant cosmos, but in the global positioning system, GPS, that guides millions of people every day. The GPS relies on a network of satellites orbiting Earth, all equipped with highly accurate atomic clocks. For the system to give you an accurate location, these clocks must be perfectly synchronized with the clocks on the ground. However, the conditions in space introduce two immediate, critical errors based on Einstein's theories. Correction for speed, special relativity. Because the GPS satellites are moving at very high speeds relative to us on Earth, time passes slower for the satellites than for us on the ground. Correction for gravity, general relativity. The satellites orbit in a much weaker gravitational field than we experience on Earth. According to general relativity, time runs faster where gravity is weaker. These two effects, working in opposition but with the general relativity effect being stronger, mean the clocks on the satellites run about 38 millionths of a second too fast every day. If the GPS software did not constantly and precisely apply Einstein's relativistic corrections, the system would quickly accumulate errors of many kilometers per day, rendering navigation impossible. Every time a car or phone uses GPS, it is executing an everyday essential calculation based directly on the general theory of relativity. 6. The unfinished symphony, the quest for unity. Though Einstein failed to realize his unified field theory, the single elegant equation uniting all cosmic forces, his pursuit remains the holy grail of modern physics. His dream was not dismissed, it was inherited. Modern physicists, working on theories like string theory, continue the quest to find the one final law that governs all of reality. The very attempt to unify gravity with the quantum world, the necessity of a theory of everything, is a direct philosophical legacy of Einstein's unyielding, lifelong belief in the underlying simplicity and rationality of nature. His work, born of a compass and a moment of quiet contemplation, continues to define the very parameters of our reality, echoing in the deepest gravitational wells of the cosmos and in the simple, necessary functions of our daily technology. Beyond physics, relativity in culture, and the philosophy of the solitary mind, Albert Einstein left the world with a universe of curved space, quantum chaos, and the ethical burden of nuclear power. Yet his influence was never confined to the pages of physics journals. He transcended the role of scientist to become a public philosopher, an intellectual sage whose ideas about relativity, objectivity, and the nature of wonder permanently seeped into the fabric of art, literature, and the common language. His legacy is found not just in the telescope's discoveries, but in the persistent, uncomfortable questions his life and work force us to ask about human reason and reality itself. The philosophical shockwave, objectivity under fire. Einstein's theories delivered a profound shock to Western philosophy, challenging the foundational assumptions that had held sway since the Enlightenment. The end of Newtonian absolutes. For centuries, Western thought relied on the Newtonian premise of an absolute external reality, fixed space, fixed time, and fixed laws that existed independently of any observer. General and special relativity shattered this assurance. By demonstrating that measurements of space and time depend on the observer's frame of reference, their velocity or gravitational environment, Einstein forced philosophy to contend with the idea that objectivity itself is subtly contextual. The redefinition of reality. Philosophers were forced to acknowledge that reality is not passively observed. It is actively constructed by the relationship between the observer and the observed. This profound shift from the absolute to the relational was one of the defining intellectual movements of the 20th century, confirming the skepticism of earlier philosophers like Hume and Mach, whom Einstein deeply admired. Second, relativity in art and literature. While artists and writers often misunderstood the technical details of special relativity, the idea of relativity, the notion that truth is contextual and fixed perspectives are illusions, became a potent defining force in modern art and literature. Cubism and multiple perspectives. The rise of Cubism, championed by artists like Picasso, coincided directly with the early discussions of relativity. Cubism sought to depict objects not from one static viewpoint, but from multiple perspectives simultaneously, a visual attempt to capture the fluidity of observation in a four-dimensional space-time continuum. Although artists often denied a direct causal link, the cultural air of the era was thick with the idea that fixed perspective was an artificial constraint. Modernist literature and time. Writers, particularly those involved in literary modernism, began experimenting with nonlinear narratives. Authors like James Joyce in Ulysses and Virginia Woolf in Mrs. Dalloway deliberately shattered chronological time, allowing the narrative to expand, contract, and loop based on the subjective consciousness of the characters. Time, in these works, was no longer a uniform clock ticking. It was a flexible, psychological river, a clear echo of Einstein's temporal relativity. Third, the solitary man and the politics of conscience. Beyond his scientific output, Einstein's public life cemented his status as a unique kind of political and moral figure, the public conscience of the scientific world. The anti-nationalist, his commitment to internationalism, and his early renunciation of German citizenship underscored a belief that science must transcend national allegiance. He saw patriotism and nationalism as the measles of mankind, tribal instincts that actively suppress the universal pursuit of truth and cause unnecessary conflict. The champion of human rights. His advocacy for pacifism, nuclear disarmament, and civil rights was not sporadic. It was deeply rooted in his philosophical conviction in human dignity and the Spinozistic belief that ethical behavior is simply the rational response to the unity of nature. His support for the civil rights movement, particularly his friendship with figures like Paul Robeson and his involvement with the NAACP, demonstrated his willingness to use his fame to confront deeply entrenched societal injustice. Fourth, the philosophy of science, imagination, and simplicity. Einstein's methods and maxims provided a fundamental philosophy of science that remains inspirational, the primacy of imagination. Einstein repeatedly stressed that imagination is more important than knowledge. This was not hyperbole. It was the core of his method. He believed that the great leaps in physics, like the Gedanken experiment of chasing a beam of light, came from an almost artistic, intuitive leap of imagination, not from simply compiling empirical data. Data confirms the theory, but imagination creates it. The elegance of nature. He possessed an unwavering faith in the simplicity and elegance of nature's laws. His lifelong quest for the unified field theory was driven by the aesthetic conviction that the ultimate laws of the universe could not be clumsy or complex. They must be expressed in a single, simple, beautiful geometric relationship. This belief in the beautiful equation guides all modern physics searches for the fundamental theory of everything. V. The enduring quotability. Einstein's ability to articulate complex concepts with simple, profound statements cemented his place in global culture. Many of his quotes, often stripped of their scientific context, became philosophical mottos for the modern age. The most beautiful experience we can have is the mysterious. This phrase underscores his commitment to awe as the wellspring of both science and spirituality. Insanity is doing the same thing over and over and expecting different results. A simple statement of the necessity of intellectual flexibility and self-criticism. The important thing is not to stop questioning. Curiosity has its own reason for existing. Reinforcement of the core drive that led to his childhood compass moment. His words became a cultural shorthand for the intellectual rebel, the humanitarian sage, and the genius dedicated to the profound simplicity of truth. Sixtus, the final legacy, humility and awe. In the end, Einstein's greatest human legacy is the paradox he embodied, the greatest mind of the century, yet a man dedicated to humility and awe. He was the personification of the solitary thinker, proving that the most profound revolutions can originate not from massive labs or political power, but from quiet, unconstrained reflection. He offered humanity the ultimate gift, a complete, rational view of the cosmos, while simultaneously reminding us that the vastness and underlying mystery of the universe are infinitely larger than our capacity to grasp them. He proved that our universe is a place of incredible geometric elegance, where time is flexible, mass is energy, and reality is defined by the absolute speed of light. The unfinished work, the lasting human and scientific testament. We conclude the story of Albert Einstein not with the finality of death, but with the boundless continuation of his ideas. His life was a testament to the power of a single, unconstrained mind, proving that the most profound revolutions in human understanding can originate not from massive government projects or well-funded laboratories, but from the quiet, persistent contemplation of one solitary thinker. Einstein's final enduring legacy rests on three pillars: his unyielding philosophical integrity, the paradoxical nature of his contributions, and the absolute necessity of wonder in the face of the unknown. The triumph of intellectual integrity, Einstein's biography, is at its heart a powerful lesson in intellectual integrity. From the moment he rejected the rigid structure of the German gymnasium to his final, isolated decades working on the unified field theory, he chose truth over comfort, conviction over consensus, and solitude over celebrity. Rejection of authority. His early success was predicated on his refusal to accept the fixed, absolute authority of Newtonian physics. He demonstrated that science must perpetually subject its deepest assumptions to relentless, skeptical scrutiny. The price of conviction. His famous isolation from the mainstream physics community over quantum mechanics was the ultimate expression of this integrity. He was unwilling to compromise his lifelong philosophical belief in a deterministic, rational universe, even when the collective weight of experimental evidence and scientific opinion moved against him. He would rather be isolated, but philosophically consistent, than popular, but intellectually compromised. This deep commitment to his own reasoned position, even in defeat, provides an enduring model of philosophical courage, the moral imperative. His political actions, his lifelong pacifism, his support for Zionism, and his passionate advocacy for civil rights were extensions of his scientific principles. He believed that if the universe was governed by a profound, rational order, then human morality and politics should strive to reflect that same order, necessitating justice, peace, and universal human dignity. The paradoxical nature of the architect Einstein's contributions are defined by a series of profound, interlocking ironies that shape our modern world. The catalyst of chaos. He was the ultimate champion of order and determinism, yet his 1905 paper on the photoelectric effect launched quantum mechanics, the field of physics defined by randomness and probability. He was the father of the chaos he spent his final decades trying to disprove, the pacifist and the weapon. The man who preached peace and fled war was the singular voice that prompted the creation of the most destructive weapon in human history. The terrible reality of the atomic bomb, powered by his elegant equation, $2, stands as the ultimate heartbreaking testament to the ethical gap between pure scientific discovery and its practical application by human institutions. The theorist and the technologist. The philosopher of pure thought, whose work was utterly divorced from laboratory experimentation, created a theory, general relativity, that is now the essential daily engine of global technology like the GPS system. His most abstract ideas proved to be the most practical. The ultimate testament, the necessity of wonder Einstein's life, was fundamentally a celebration of intellectual curiosity. His journey, which began with the mysterious, unseen force guiding a compass needle, was a lifelong effort to recover and quantify that initial sense of awe. He famously articulated that the highest form of human experience is the perception of the mysterious, the recognition that there is an order and an ultimate logic in the universe that transcends our immediate grasp. His quest for the unified field theory, though technically unsuccessful, was the final, dedicated expression of this cosmic religious feeling, the belief that the universe is not malevolent or indifferent, but simply sublimely rational and waiting to be understood through disciplined thought. Thus, the eternal unfinished work of Einstein passed away, leaving his unified field theory incomplete, a final set of equations still unresolved on his hospital bedside table. Yet, in the failure lies the final great lesson. The work of science is never finished. His unanswered questions, how to truly unify gravity with the quantum world, remain the driving challenges for physics today. Every new gravitational wave detected, every experiment in particle physics, and every new cosmological model is built upon the foundation he laid, and every quest for the theory of everything is an attempt to complete the geometrical symphony he began. His theories of relativity did not just change physics, they redefined humanity's place in the universe. They showed us that reality is deeper, more flexible, and more interconnected than we ever imagined. The genius of Albert Einstein lies in the simple, profound legacy he left for all of us. The unwavering courage to ask the fundamental question, what if? And the dedication to follow the answer, no matter how much it challenges the boundaries of our known world. The ultimate conclusion is that the universe he described, curved, expanding, and teeming with silent, unseen forces, is the enduring monument to the quiet architect who found the grand design of the cosmos in the solitude of his own mind.